Good morning everyone, and I'm here to present my report on analysis of microprocessing element. It can be either microprocessor, controller, or IP core, whatever it is, from any vendor of your choice based on the concepts learned in the computer organization and architecture syllabus. So again, this is SUBHASHREE Panda. So what I have selected as my microprocessor is CORTEX M55. And it has been recently launched on February 20, 2020. So CORTEX M55 is an ultra-low power ARM microarchitecture designed by ARM Holdings for microcontrollers and embedded subsystems. This microarchitecture is designed as a synthesizable IP core and is sold to other semiconductor companies to be implemented in their own chips. The CORTEX M55, which implements the ARM v8.1M ISA, is an ultra-low power core which is often found in microcontrollers, low-power chips, and in the embedded subsystems of more powerful chips. And the CORTEX M55 processor is the first ARM Cortex-M processor supporting the ARM v8.1M architecture. With Helium technology, CORTEX M55-based products can achieve a significant increase in performance and energy efficiency on signal processing and ML machine learning applications compared to the previous CORTEX M-based products. And just quite a short overview over this processor. The CORTEX M55 is designed to deliver outstanding performance and energy efficiency for control, signal processing, and ML with a small silicon footprint. Meanwhile, the design continues to align with the key requirements you will find in microcontrollers and embedded systems today, including the real-time capabilities, security, and the ease of use. So this is our clear block diagram of the microprocessor. You can see each and every important component, maybe the NVIC, the WIC, then MPU, PMU. So this is the complete block diagram of our CORTEX M55. And now we were asked to give the internal diagram of each and every block. So these are a few blocks which I had drawn. The flowcharts, they have been drawn by using the appropriate software, and that is Chart, and it is very user-friendly. So as to say, you can say it is a very user-friendly app, and you can download it and you can use it. It's just draws each and everything very easily, very simply. So that's it. So this is your NVIC block diagram, then your FPU floating point unit, then going to the next component, that is your coprocessor interface. So these are all handmade diagrams. And if possible, I will go and show you just one of my diagrams, how it is, like how come it is user-friendly. I will just do it. So now coming to the most important part of each and every, whenever you can say, like whenever you hear the name of any microprocessor, you always go to the instruction set. They are the building blocks, so as to say. These are quite some of the instruction sets for the CORTEX M55 microprocessor. So I guess there are overall, let's see how many. Oh my god. Oh, there are many of them. So when are we going to reach the end? Okay, yeah, I got it. There are totally 266 instructions in the CORTEX M55 processor. Wow, good. And we can look at some of the instructions. So ADC, add with carry, ADD, they just are used for adding numbers, and like that continues AND, which is used for logical. And now you see this ASR, arithmetic shift right. the resistor write shift operations move the bits in a resistor right by a specified number of bits, and that is the shift length. So this is what this answer does. It shifts the resistor value right by a variable number of bits, shifting in copies of its sign bit, and writes the result to the destination registers. And like ASR, which is arithmetic shift right. So like that, likewise we have LSR, which is a logical shift right. It shifts the resistor value right by an immediate number of bits, shifting in zeros, and writes the result to the destination resistor. Now you can see the ROR over here. I'm just quite looking at a very few instructions just to give like what all these things do. So ROR, this instruction is rotates right, just rotates the resistor value by a variable number of bits, inserting the bits that are rotated off the right and into the bracketed bit positions on the left, and writes the result to the destination register. And there are many of them. There's instructions like CLJ, they are the count leading zeros, and the CLJ instruction, it counts the number of leading zeros in the value in RM and returns the result in RD, and the result value is 32 if no bits are set, and 0 and if the bit is set. Now CMP, you can see the CMP command there just for compare, and there is CMN. CMP and CMN, one is compare and compare negative, and these instructions, they compare the value in a resistor with operand 2. They update just the conditional flags on the result, but do not write the result to a resistor. The CMP instruction subtracts the value of operand 2 from the value in Rn, and this is the same as a subs instruction, except that the result is discarded. And the CMN instruction adds the value of operand 2 to the value in Rn, and this is the same as an ADDS instruction, except that the result is discarded. Henceforth, these are going to be your instruction set, and as I've discussed above, that there are 266 instructions altogether. And as per the architecture of this CORTEX M55, it uses RMB 8.1M, as I've already told, that this is the helium is a new vector instruction set extension in the RMB 8.1M architecture that enables a significant uplift in DSP and ML capabilities. So it uses a 64-bit internal bus. The performance has already been given, and it has been compared with respect to the M4 and M7 microprocessors. The pipeline is of 4 stages, which is 2 into external interrupts, and the FPU is new half precision support. The TCM is 64-bit AHB DMF4 to crossbar interface, and the bus used over here is AXI5. New coprocessor interface support, new custom instruction, new helium extension support, etc. And memory hierarchy has been seen over here. It has a private L1I, L1D, ITCM, and DTCM. And all the 4 are configurable in size. So this is the memory hierarchy as it has been given. So this is how this microprocessing elements architecture has been correlated, either comparing or the similarities or the differences, whatever, according with respect to the architectures of von Neumann or Harvard architecture has been listed over here. Then going to the resistor organization of the microprocessing element, there are several resistors found in this CORTEX related to this CORTEX M55 microprocessor, that is core resistors, and under core resistors several categorized by general GP or general purpose resistors, stack pointers, stack limit resistors, link resistor. Link resistor, it actually stores the return information for subroutines, function calls and exceptions, and program counter. It contains the current program address. And the PC is the resistor R15. It has been listed here. Then combined program status resistor. These all diagrams have been used by using inappropriate software. Then control resistor, as per the name, it controls the stack that is used, the privilege level for software execution, where the curve is in frame mode and indicates whether the FPU or MBE state is active. Then system registers, here comes your system registers. They are just a combination of system control, implementation control, and implementation defined memory system and power mode control registers. So this is it. So this all things we have discussed about our register organization in our microprocessor CORTEX M55. Coming to this type of algorithm used over here, same as per goes for all the microprocessors. There are 16 general purpose register and they are all 32-bit wide. That is on CORTEX M55. And all the microcontrollers, they have a set of registers. So as per the maths instructions, the destination is equal to source 1, then operation performed, and then source 2. As we have very well gone through this instruction set, LSR and LSRs, they're often used for unsigned values, and to shift right we use the ASR and ASRS, and to rotate the family of registers, instructions used are ROR and RORS. And this RRX and RRXS instructions, they are just, it does not update the flag, so to say. It does not update the carry flag either. However, it still reads the carry flag, so the result of the above operation will be the same. And eventually, if we come to the add operation, the add instruction is used, and for multiply, mul operation, mul system instruction, they are used, and for division, SDIV or UDIV, they are used. So this is all common for all the microcontrollers. Here we have discussed about the signed operation, unsigned calculations, the type of algorithm used in this microprocessor. Now coming to this control logic unit used in this CORTEX M55. It has a 64-bit ALU, I've already told, and the CORTEX M55 can perform 2 into 32-bit, 4 into 16-bit, or 8 into 8-bit max per cycle, and it has been compared with our existing, whatever we have been studying in our chapters, that is hardware control unit and microprogram control unit. It has been compared with it, and then coming to this memory management system in our microprocessor, I would like to say the CORTEX M55 memory system is very similar to the one in the CORTEX M7 processor at a high level. However, the details are different. The internal memory system is designed into two parts, a closely coupled part that is optimized for real-time deterministic behaviors, then a cache-based bus system that enables the CORTEX M55 processor to be used with memory systems with higher latency. So this is it. This is the MPU, then the security attribution unit, the TCM, and yes. So this is the block diagram. This is the flowchart of our memory management system. Now coming to the pipeline over this microprocessor. The pipeline is divided into two sides. The main pipeline, which is always present, and the extended processing unit, which is present only if the FPU or the helium support is included. The separation of the pipeline allows the FPU or the helium unit to be powered down or placed into retention state if they are not being used. And the 4-stage pipeline used in this microprocessor enables this CORTEX M55 to have a modest increase in the maximum clock frequency compared to the popular CORTEX M4 processor, which is typically over 10% depending on the configuration. So this is the first stage in order scalar pipeline design. Now the extended processing pipeline, the FPU unit is based on the ARM FPD5 architecture. And yes, and the processor level parallelism whether present or not. So answer is obviously no. It does not support any processor level parallelism. Then the cache coherence protocols are MOSI protocol. The key interface in this processor is the instruction cache and the data cache. The instruction cache is optional and data so is the data cache. It can be configured from 0 KB to 64 KB when implemented, and the data cache can also be configured from 0 KB to 64 KB when implemented. It is just based on a 4-way set associative cache mechanism, and it supports the write back and the write through WB and WT cache policies and optional ECC. All the bus interfaces are based on bus protocols defined in AMDA standard, and these bus protocols, they are open, royalty free, and are proven in products in the market today. To help the chip designers deal with the system level integration, ARM also provides the ARM Custom 300, a reference design that includes various system IP components for the Cortex M55 processor. So this is how I completed my report on the microprocessing element, that is CORTEX M55, and there we go. Now I'm going to attach how I have drawn my flowcharts using an appropriate user-friendly software, which I would strongly recommend people to use it as frequently as you can if you come across with this kind of projects in your colleges or schools. So right now, after completing this, I'm going to attach that video of